I was not. Okay, so now I am. All right, so once again, NH4 plus, we have 8 electrons. We use bonds, right? The next thing to do is use the bonds. We have 8 electrons used. Nitrogen has 8 around it. And remember, hydrogen is an exception and it only likes 2 around. Hydrogen will never have more than 2 electrons around itself. And since this is a bond, right, that means it's between them, then you have 2 electrons that are being shared by both of them. So each one of them has 2 electrons as it's supposed to be. So you have 0 left, and that's correct. Yes, ma'am. Oh, nothing. Okay. So the last thing to do is to put the brackets around it, right? And to label the charge. And there you go. All right. Now, there's another thing called resonance along with this. Resonance basically is a way to represent a molecule that has multiple Lewis structures, and you represent it by multiple ones rather than a single. So what you do is the actual structure is the average of all of the possibilities, which in an advanced class, you can actually do it a little different, but this is not. So we're just going to do it like this. Hello? You still there?
Thank you, love.
Okay, no, but I'm just saying, okay, I'm gonna make sure everybody's still here because you all disappeared on me. So, okay. So then you show the possible structures separated by a double-headed arrow. Why double-headed? That means that you can go either way, up or down, right or left or whatever. And that's what that means. So if you notice, this one right here is O3, and that right there is the bonding where it shows the double bond is on the left, but over here it's on the right. So see, this is what we talked about being different. So this is exactly what this is. It is a second structure that is possible. All right, so let's do SO3. Let's do all the math and all that good stuff. So I'm going to draw directly on here. Okay, so we have sulfur, right? We have 1 times 6 equals 6. Oxygens, we have 3. No, sorry, 1. 3 times 6 again equals 18, right? That gives us a total of 24. Now we make our little structure. So we do an S, 1, 2, 3, O, O, O. That takes away 6 of them. So we have 18 left. Now see, sulfur is not going to like, let me make this in red. I want it in red so we can see, because that's blue and this is blue. Okay, so sulfur is going to get 6 electrons, and that's not enough. But remember, we always have to do the oxygen ones first, and you will see that we don't have enough. Once we do, oops, yes, I'm doing that one. That's not a good one. Okay, and you notice I'm strategically placing them around in pairs and not just anywhere, right? They go like a little box. So you want to make a little box around the atom. Okay. So they're on top, on the side, and on the right and on the left, and that's it. And on the bottom, just depends. Oh, and this one's top, right, left, and this one's left. Right, top, bottom, and left, right, bottom. So yeah. Anyway, so right here, we have 16. So we can see that we're going to need to do one of our things that we do, and that is add a second bond. See, we had the same amount of electrons. All we did was relocate the lone pair into the bond. That's all. So now this is the correct structure. But since this is the correct structure, couldn't that double bond be here or here too? Yes, it could. So in order to represent it, what we do is we write it like this. See? Because we have 3 different clines. All right, and that's that. We're going to stop there and we're going to go on to the next part. Now, that is Lewis structures. Now, from Lewis structures, you can tell 2 things. You can tell the molecular geometry and you can tell the polarity. Okay, for the molecular geometry, you have to look at the VSEPR theory, which is valence shell electron pair repulsion theory, which states that electron pairs will orient themselves so as to minimize all of the repulsion that would happen between electrons if they didn't. So to do that, they want to get as far away from each other as possible. And as possible depends on how many things are around the central atom. So in this case, you only had 2 atoms, so they're going to opt for 180 degrees. But there are 2 types of electron pairs. You have your bonding pairs, which are your bonds, right? The ones that we represent by lines. Or if you see them in other Lewis structures, sometimes you'll have the 2 electrons in the middle of the 2 atoms, and those are bonds too. But I like to put lines because it's easier to tell which one's which that way. And then you have the lone pairs, which are the ones that are not around any other, between 2 atoms, but they're around just one single atom. And to know this, lone pairs repel stronger, more, they are stronger, so they repel more than bonding pairs. What does that mean? That means that the lone pairs, if they're present, will reduce the bond angle between the atoms. Let's look at that. So how do we determine molecular shape? First thing to do is to draw the Lewis diagram, which is what we just did. We learned how. Number 2 is to tally up the pairs and looking at it, see what kind of, and pairs. By pairs, I don't like the word pairs. I really should call this areas of electron density, because the word pairs indicates 2. And if you have a double and a triple bond, you're going to have 2 and 3 pairs, right? So people are like, okay, wait, that's not right. So what we're going to call these is areas of electron density. Okay, areas of electron density. So a double or triple bond is still just one area. You see, that makes more sense. And the shape is determined by the number of bonding pairs and lone pairs. All right, so let's clear that. And there are 8 common shapes. So here's the first one. You have 2, 2, and 0 lone. So it looks like that. This is what is known as a linear shape. The bond angle is 180. Now, the other thing that's not on here, which I always like to use, is what is known as a type. And the reason I do this is because to me, this is easier to look at. So you have a central atom, which is what this is, 2 bonds. You see that? Central atom, 2 bonds. These are the bonds right here. Let me put them in a different color so you can see the bonds. See? So AB2, central atom, 2 bonds. The bonds are the yellow. Okay, just clear that. And so this is an AB2. Just remember that. And an example of that would be this guy. There we go, beryllium hydride. All right, so there you go. That's one. Now we have the second one. And this one is a 3 bonds, no lone pairs. And it looks like this. Come on. It is known as a trigonal planar. And the angles between each other, so from here to here, right, is what we're talking about. From here to here. Oh my gosh, this thing is not letting me do this. The angle is 120 degrees. Okay. And from here to here too, and from here to here too. So they're 120 degrees all around. All right. And this one I like to call an AB3 because you have one central atom and 3 bonds, right? All right, so clear that. An example of it is BF3, boron trifluoride. All right, so let's go next one. Now this time you have an AB2E. Okay, what do we call AB2E? Let me show you. Central atom, bonding pair. There are 1, 2. And then you have 1 lone pair. So it's called an E. See? So it makes it AB2E. Let's clear it up. An example of this would be, oops, come on, mouse. Bent. The name of it is called bent, but this is a bent that comes from 120. So remember this much, because there are, or a bent that comes from the trigonal planar. There are bents that come from another kind. And so the bent in this case is 100. The original angle was 120. But remember, this lone pair is making this get closer to each other. So the bond angle is going to be less than 120. And an example of it is SO2, or sulfur dioxide. Okay, let's clear that. Let's go to the next one. 4 total, 4 bond, 0 lone. Okay, so in this case, you have 4 total atoms that are bonded to the central atom, 4 bonds, and no lone pairs. So this is an AB4, right? That makes sense. AB4, because A for its central atom, B for the bonds, and there are 4 of them, right? All right, the angle here is 109.5. So if you can imagine this, this is like a little pyramid. And guess what? That's the name. Its name is trigonal pyramid. I mean, sorry, tetrahedral. Sorry, wrong one. I'm thinking of the one ahead. Tetrahedral. This is a tetrahedral. Why is it a tetrahedral? Because if you were to draw this shape, it would have this look to it. You see that? You would have like a little tetrahedron on there. So that's just the first 2 faces. The other 2 faces would be in the back. But anyway, so that's all right. The next one that we have is an example. The angle, like I said, is 109.5. And here's an example, CH4, which is called methane. Now, if you think about it, the carbon would be in the middle, right here. And, oops, sorry. The carbon would be in the middle right here. And the hydrogens would be outside. All right, so let's clear that. And I go next.
I wonder where everybody went.
I don't know. Well, like I said, if you don't show up, there's nothing I can do. I mean, I have to keep going. That's all there
Right,
is
because this
to it.
is especially is super
Yeah, I know, but I mean, it is what it is, right?
right.
A, B, 3, E. Why A, B, 3, E? Well, you have 1, 2, 3 bonds and 1 lone pair. You see that? Okay, so that's what that is. A, B, 3, E. It tells you a central atom, that's A, B for bonding, and E for electron pairs. And there are no there's 1 electron pair in this one. So in this case, our shape is going to be trigonal planar, trigonal pyramid, which is a little pyramid. If you actually think about it, it's like looking at a little pyramid right here. Look. See? And if you imagine the back, it is exactly the same too, right? All right, so clear that. And let's keep going. In the angle for this one, remember this one makes it smaller, right? So since that one makes it smaller, this right here makes it smaller. This this big goose egg right here makes it smaller. So these get constricted, right? All of these angles get constricted, every one of them. So it becomes a trigonal pyramid, and the angle of it is not going to be what you think. It's not less than 109. Yeah, it is, but there's an actual number to it. It is 104. 107, sorry. 104 is the next one. 107. So this is the usual. And an example of it is ammonia, because you do have the lone pair for the ammonia on top, and then you got the NH3s. All right. Common molecular shapes number. Last one of the ones that we really need to worry about. So here it is. 2 lone pairs, 2 bonds in a central atom. So once again, this one's going to be an A, B, 2, E, 2, right? Because we got 2 of these, this one and this one. That's the E's. And this one and this one are the B's. You see? So that's an AB2E2. Now, let's keep going. And some people call it other terminology. That's just mine. And of course, this angle is going to be even less than the one before, right? Because you got 2 of them pushing against it. So that angle is 104.5. And an example of it is good old water. Water is very polar. All right, so that's these are the other ones. I'm not going to talk too much about them, but these are all expanded octets, and you need to look at these later. But just to know that they exist and to know their name. So the first one is this one, and it's called trigonal bipyramid, and those are the angles. 120 between the central 3 atoms and 190 on the ones that are the up and down atoms. That's a PCl5, an example. Another one is a 660, and this one is known as a octahedral because it makes 8 sides. And this one is a all 90 degrees. An example is sulfur hexafluoride. And okay, so let's look at these. All right, so the first thing to look at is what's around the central atom. So we know that we have a central atom, right? So we know that this is an A. We have 1, 2, 3 bonds, right? 3 bonded atoms. And we have 1 lone pair. So that's the type. Okay, since we know that it's an AB3E, if we had taken notes, right, we could go back and we say, oh, this is what is known as a trigonal pyramid. I'm trying to write it on the place where you can write it. All right. And the angle for this one is 107. We know everything about it. There's Jocelyn. Okay, so that's how you do that one. It's clear. And there's a, let's see.
Is Jocelyn here?
Yes, I know. I said there she is. All right, so there you go. See, we knew. And that's the kind of the shape of it. And here's another one, CO2, okay? So what do we have? We have one central atom, an A, right? Remember? And two bonds. We're just calling them B2. Remember, each area of electron density, right? Okay, so it's an AB2. There's no E because there's nothing around the central atom that is a lone pair. So this makes it a 180 degrees, and it is known as a linear shape. And that is what we have, if you look. Okay, let's do the mouse. Okay. Oh, sorry, clear. Clear that. All right, so see two bonds, zero lones, all of that tells you the shape. It's linear, 180. There you go. And that's how you do these. All right. Now, the next part is the polarity. How do we know if something is polar or non-polar? Well, first of all, they have to be covalent, mostly. Well, not necessarily. They can be non-covalent, but ionic are always polar. So that's why I'm not saying that, but because they're not really called polar, they're more like ionic, right? So we're not gonna call them that. But you have to have what is known as a dipole moment. What is a dipole moment? Well, a direction and the polar bond in a molecule. So if you have a polar bond, and all of the bonds are going to be polar, because there's always going to, unless they're the same element, then no. But the arrows are going to always point toward the more electronegative atom. Remember, electronegativity and the periodic table increases this way, right? And the most electronegative atom is fluorine. So hydrogen is way over here somewhere on the right. So this tells me that my bond, oh, sorry, let me do it in red, undo that and change this to red. Okay, that my bond is gonna go this way. All the electrons are gonna be pulled more towards chlorine. And this is what is known as a partial charge. So we always put that. All right. So in order to know if this is a polar molecule, which it is, you would have to know which whether these forces are going to cancel or not. Well, this one is not because there's only one, right? And so it's going to always go towards the chlorine like that. And which results in a partial positive from the hydrogen because the electrons are closer to the chlorine, and a partial negative from the chlorine because the electrons are also closer to it. So that's how it looks. All right, so let's do another one. Oh, let me clear that. All right, so determining the polarity depends on the dipole moments and in the molecular shape. So non-polar molecules are symmetrical, like this one. Remember, whenever we're talking about polarity, we're talking about dipole moments that form. And there's this one going up this way. Oh, it's not letting me draw. Ah, that's because I got the stupid thing on. Okay. There's this one also going this way. And there's this one also going that way. And if you look, this is very symmetrical. And these two are going to cancel that one out. So when you are looking at adding vectors, which is what these are, you always look at the direction and the magnitude, which is this is a scalar. Yeah, it's not a scalar, it's a vector. So we are going to, when we add it up, we get a 0 momentum. Okay, see, just like I showed you. All right. So one of the main things, remember this, dipole moments are asymmetrical and they do not cancel. For example, this one, oxygen and hydrogen. Oxygen is more electronegative, so the two are going to come this way. And see, there's nothing there that cancels those. So you're going to actually end up adding up like that. So you do have a dipole moment here. And the partial positive goes on to the hydrogens, right? And the partial negative goes on to the oxygen. And that is how you do that. Okay, so with this, see? All right. So how do we know if something is polar or not? Once you do the Lewis structure, if you have an asymmetrical shape, which means you have a lone pair, very important. Any lone pairs will create asymmetry. Or this is the other one. You have asymmetrical atoms. You notice one of these is different from the rest. This one is. So then your polarity is going to go like this. And see, now it adds up to negative. You see? Because if this would have been another chlorine, all of them would have canceled. So there are no lone pairs, but the hydrogen is imbalancing everything. Okay? So that is how you do those. Okay, let's see, clear these. And let's keep going. So you end up with a net dipole moment. Okay, so close this out. No, if I close that out, I know what's going to happen. It's what happens to me every time. So I'm trying not to do that. All right, so if we were to do the VSEPR lab, we're not going to do all of it, but you notice that this is a resource right here to help you do some answers for we normally would have done this as a group and would have had more time, but you know, like I said, if you guys don't show up to class, I can't teach, you know, and to anybody. So I should have just kept going, but instead I waited, and now we're to where we should have been long time before. Now, when you have intermolecular forces, okay, that's another part. You have 4 types, and I'm just gonna go over them, and you can watch the PowerPoint. Let me see which one it is, the one I prefer. There are others, but the one I prefer to explain the intermolecular forces is purple. Yeah, this one. This is the one. It's kind of purple, like grape color purple. Yeah, and these are your 3 right here. Okay, so with these, what I'm gonna do is I'm gonna add some quick stuff that you want to write down. Let me go ahead and enable editing so I can do this. Okay, I'm going to add really quick some text to each one. Okay, so London dispersion forces, they occur in all molecules. Okay, polar and non-polar. Did you hear that? Okay, non-polar. Where's my non-polar? Okay, so I'm just gonna stretch this out. Oh no. Oh well, you can read that anyway, right? Yeah. But I think I'm
Yeah,
gonna use a different color. Maybe red is not gonna work. Blue is not gonna work. How about lighter blue? Lighter blue might work. Okay, so dipole occur between polar molecules. Period. Remember that you can see that better, right? Ion dipole occur between charged molecules and polar molecules. Okay. There we go. That's what I wanted to do. And hydrogen bonding. This is a special type of dipole that occurs only between hydrogen and, this is where you got to remember, fluorine, oxygen, and nitrogen. So hydrogen has to be present, hence the name hydrogen bonding, right? But it only occurs between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen, okay? Hydrogen always has to be there, okay? So that's what you want to remember, okay? And now we're going to apply all of these together into a couple examples. Just make sure you take a picture of that or whatever, because that's the one time I'm going to write it in. All right, you got it?
yeah.
Okay, I'm clearing it. All right, so next. All right, we're going to now go to the, it's not letting me. Come on, escape. There we go. All right, so now it's letting me go to where I need to go. Okay, I didn't want that one. Okay, so I was going to look for this one, the VSEPR lab. Okay, so for this one, we have some things to fill in. Okay, and it explains to you the whole thing again. And this is what we were going to do, you know, in class together as a group. And there's either three or four of you that we're going to do it. And it even has a table. You see this table? This table is very important to what we're going to do. So you need to always look at that table, which is on page 2. And it tells you the procedure for drawing Lewis structures. It goes over it again. And then you got the AB2 and all that stuff that I sound. Okay, so here we go. I've done one. Now, the one thing I cannot draw on here, right, but I'll draw it to the side, is the actual Lewis structure. But I can do all the calculations and all of that. I can do if I told it to. Did I say I could do editing? I think I did. Let's see if I can. Yeah. Okay. So for boron, boron is in group 3, right? So there's 1 boron times 3 equals 3. And then we got, who is next? Fluorine. So there are 3 fluorines times 7, because it's in group 7. That equals 21. That gives me a total of 24, right? Now, okay, so we know that. So we're drawing now. So we got the boron, we got the fluorines. Remember how we do that? We place them around the central atom, and then we make bonds. 1, 2, 3. These 3 bonds now have used 6 of my electrons. So I have to go back to here, and I have to say, okay, now I need to subtract 6, right? And that gives me a total of 18, right? All right, so I have 18 electrons. What do I do with them? Well, my next thing is to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And you're probably thinking, but boron only has 6. Yes, but boron's in group 3, and 6 is good for it. So this is the Lewis structure. That's what would go here. So this structure right here belongs right there, right? All right, I'm just gonna undo that. That's where it goes. All right, so now that we can look at it, we can say, how many electron groups do we have? Well, we have 3. Oh, no, I don't want text, I want mouse. Ah, go away. Mouse, mouse, mouse. We have 3, right? And according to that, this is an AB, and this is one of the first things that I like to do, AB3, right? So since it is an AB3, we have 3 bonded atoms also. So the electron group geometry is different sometimes, not always, from the actual geometry. So the electron group geometry is given to us by the number of electron groups, and that is 3, which means this is a trigonal. Okay, and the same number of electron groups is the same, all of them are bonds. So once again, this is a trigonal planar. And here is our bond angle, 120. Now, do we have resonance structures? Remember, resonance structures are those that we say you have a double bond, we have no double bonds, so no. Or you can put no, none, right? And then the last thing is it polar or non-polar? Well, it is symmetrical, so the answer is non-polar. And what forces? Remember the only ones, and I'm just going to call it LDF, London dispersion forces. The only ones that are non-polar forces are London dispersion. They only come in the non-polar. All right, so let me clear these and go to the next one. Okay, so we have SO3. All right, let's do the tally. Tally for this one is going to be, no, I don't want text, I want my mouse. Let's go. We have 1 sulfur, right? Times 6 because it's in group 6, and that equals 6. And we have 3 oxygens, and they're also in group 6. So that's going to be equal 18 for a total of 24, right? All right. We have no, okay, so when we are doing the bonds, right, we're going to draw it, and it's going to be S, oh, no, not like that. S, and then we have 3 O's. Oh, sorry, clear. Undo that one. That's an ugly O. And then we got bonds. So we use 6, right? Because the bonds use 6. Remember, that's what we're looking at. So we subtract 6 from this one, and that gives us 18 again. All right. Look, it's looking a lot like BF3, isn't it? But the problem here is the central atom. And you'll see 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. Well, yeah, that's good. We have 18. But sulfur is not an exception. Sulfur needs 8, and it only has 6. So what we do is we take one of these and make it into a bond. Remember, that was part of that second one. So yes, now that we have that, that is the Lewis structure that belongs in here. Remember that. All right, so how many electron groups do we have? Well, we have 3, right? We only have 3 electron groups. We have a double bond and 2 single bonds. So that means that this is a trigonal planar. How many bonded atoms? We only have 3. That means this is an AB3 also. And that makes it a trigonal planar. The bond angle is still 120. And there are resonance. Yes, there are 3 resonance structures. Remember, resonance structure just means that we can take this double bond, right? And we can move it to here also. Or we can also move it. And remember, when we move it there, we have to adjust the, oh, sorry, the lone pairs, which I meant to do bigger. There we go. But we now need to adjust this one, right? So there you go. Or it can look like this. Let me see, eraser, boom, boom, boom. Okay. Oops, wrong one. Undo that one. And now do the big ones. Okay. See? So it can run around in 3 different spots. So that's why we say we have 3 resonance structures. All right, next one. Oh, and we're not done yet. Oops, sorry. Mouse. This. Okay. All right. So what's next? Okay, is it polar or nonpolar? Well, it is a nonpolar. Why do we know it's nonpolar? Because it has no lone pairs around the central atom. So the only force is London dispersion forces. This is pretty simple, right? So far, so good. All right, next, we've got the CO2. Okay, let's do CO2. Okay, we have 1 carbon with 4 electrons. That gives me 4. How do we know it's 4 electrons? Remember, you that just got here, we look at the group number. Group number is that 4A that is above the whole column, right? All right, the next thing is we have oxygens. We have 2 oxygens and we have group 6. Therefore, this is 12 for a total of 16, right? 16. Okay, so we got 16. So let's do the structure that we know, carbon, oxygen, oxygen like this, right? So we take off 4, right? That's our next thing. Why do we take off 4? Because we use 4 with those bonds. Okay, so that gives us a total of 12. All right, so now we place the 12 around the oxygens because that's how we do it. We do the outer atoms first, and then we worry about the lone pair, the central atom. Okay, so that's 12. All right, we have used up all of our electrons, and carbon is definitely not a happy camper. Why is it not? Because it doesn't have 8 electrons around itself. So we need to erase this one, and it becomes a double bond. Now carbon has 6, it's still not happy. So we do the same thing on the other side. We erase, it doesn't matter which one you erase, as long as you erase 1 pair. And it comes here. Now, that is the real Lewis structure. And if you ever want to check if you did right, you started with 16 and you should end with 16. So you got 1, 2, 3, 4, 5, 6, 7, 8 pairs. So that's 8 times 2 is 16. So you're good. All right, Lewis structure, like I said, goes here. How many electron groups do we have? We only have 2. How do we know we only have 2? Because we have 2 double bonds. That's it. There's nothing else around that central atom. There are no dots, nothing else. And this makes it linear. Okay, so still bonded atoms, we only have 2. So that means this is an AB2, right? And the molecular shape is still linear, hasn't changed. And the angle is going to be 180. Do we have any resonance structures? No, because they're both double bonds, so they can't move around and become one on this side and one on that side. It's still nonpolar because we don't have any lone pairs. So once again, the only forces that can have is London dispersion. All right, let's look at ClO2. Let's clear these. and look at ClO2. All right, so remember, there are two things to remember with this one. We have a charged atom, which means that we have to remember that we need to add one more electron to the total. All right, so we have one, oops, sorry, 1 times 7, because chlorine's in group 7, equals 7. And then we got 2 oxygens, right? Times 6, which is equals to 12. And then we have 1 extra electron. And that one we're just gonna, no, we're not gonna tab it there, sorry. We're just gonna add it here. And one more, right? And just, I know it's not a perfect setup, but I'm trying to get it to where they line up the way they're supposed to, but they're not lining up. There we go. And then 1 here. There we go. Now I can move it over a little bit. All right, there we go. Now, when we add it up, that is 20, correct? All right, so our total is 20. And we used 4 electrons, 2 electrons for, 4 total electrons for the bonding, right? How do we know we use 4? Well, we have to draw. So I have to draw before I do that. Okay, so we got your Cl, and you got 2 oxygens, right? That's what the crude sketch is. That's why you make a crude sketch, so that you know how many to subtract. Okay, so once you subtract it, right, you get equals 16, right? That's how many. All right, 16 electrons. Let's distribute those electrons around here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And there you go. Now, don't forget that according to our thing, we have to put brackets to have a correct Lewis structure, right? And that's your correct Lewis structure. Now let's analyze what we're looking at. All right. Oops, let me go back to my notes. Okay. So for this one, we have how many electron groups? 4, right? Because we have 2 lone pairs and 2 bonds. So we got 4. That means this is a tetrahedral structure. Normally. Oops. Don't do that. Sorry, I was just going to copy so I don't have to retype that. Okay. So, but actually, I don't need to copy it. How many are bonds, though? Only 2, right? So that means that this is an AB2, E2. First E we've had. So what does this mean? This means this is a bent. The angle for a bent coming from a tetrahedral is 104.5. And do we have any resonance structures? No, because we do not have double bonds. Is it polar or non-polar? It's polar. Why is it polar? Because we have lone pairs around the central atom that would make this an imbalance of charges. Now, what kind of things do we have? Okay, here we have a lot, because we have the London dispersion forces that are always present in every molecule. So might as well just write London dispersion for everybody. We have the dipole, and we're just going to call it DD. We also have ion dipole. Why do we have ion dipole? It is charged, right? If it's charged, it means we have ion dipole. And do we have hydrogen bonds? No, we don't. And that's it. That's what we know. Okay, let me put this one on the bottom. So there we go. So that's how we do the analysis of the whole thing. All right, let's clear that. And we are going to, there's only one more that I want to do with you, and that is not this page or this page or that page, is this page. Let me bring these down. Okay, so for these, we're going to do the same thing. All right, so I want you guys to try to do them as I do alone, right? So the very first thing to do is do the crude sketch, and that's an N with 3 H's around it, right? And you got bonds to each one. Okay, so the calculations are going to look like what? Okay, so we got 1 nitrogen, and that has group 5. So that's going to give us 5. And we have 3 hydrogens times 1. That's going to give us 3. So the total is 8. 8, but we use 6 of those, right? Which is going to give us 2. And remember, hydrogen is one of the exceptions. It doesn't need but 2 around itself, and it already has 2. So the last ones are going to go there. So the Lewis structure is this. How many electron groups do we actually have? Well, we have 4. What is the electron group geometry? It's tetrahedral. How many bonded atoms? 3. What is the general formula type? AB3E, right? Because we have 1 lone pair. What is the molecular shape? This is known as trigonal pyramid. Remember that? What is the bond angle? 107. All of that is in that table that I showed you. Do we have any resonance? No, because we have no double bonds. Is it polar? The answer is yes, it's polar. What intermolecular forces do we have? Well, we have London dispersion always, because that's always there. Dipole, dipole. We have hydrogen bonding also. Why do we have hydrogen bonding? Remember at the beginning, I showed you that it had to be bonded to either nitrogen, which it is, right? Oxygen, like in water, or fluorine. And this one is bonded to nitrogen. So yes, we have hydrogen bonding. It is not charged, but if there was an ion around, it would induce an ion dipole because it is a dipole. So it could have this interaction depending on where it's located, okay? So this one's an if, okay? But the other ones, it exhibits itself. The ion dipole is not a true statement, but it could. All right, H3O plus. Let's do that one again, okay? So we know that the oxygen is in the middle, and we have 3 hydrogens around it, right? And we have 1, 2, 3. All right, so to do the tally, we say we have 1 oxygen in group 6, gives us 6. We have 3 hydrogens in group 1, it gives us, group 1, it gives us 3. But we also have a positive charge, so we need to subtract 1. Why do we need to subtract 1? Like I said, we have a positive. When it's positive, that means we have 1 less oxygen and 1 less electron than we have. So the total is actually 8. 8, okay? And we have 3 bonds, right? Minus 6. It's going to be equal to 2. Okay. So that's how many electrons we have to put out. And it's good because oxygen is the only one that needs them. Because remember, hydrogen does not have, if you ever see this, that's a mistake, okay? Hydrogen can never have that, ever. So no, don't do it, okay? All right, so that's our Lewis structure. Now let's look at the electron groups. What are they? Well, we have 1, 2, 3, 4, right? 3 bonds and 1 lone pair. So that's 4. That means this is a tetrahedral. That means we have 3 bonds, yes? And our general formula is AB3E. And guess what? Look, it's exactly the same as the one next to it. So let's just copy it. Everything is there. 107. Everything's the same. And we do not have resonance structures. So is this the same? Well, let's see. We have polar, yes. And like I said, this one right here, let me put it in red because it's not a true statement. I mean, it doesn't have it, but it could induce one. Whereas this one, oh, and I forgot one thing that you always should do. You should always put your brackets so that you know that that's a charged molecule. All right. So we have, definitely we have London dispersion because that's always there. We have dipole because this is a polar molecule, right? We have ion dipole because this is a charged molecule. And we also have hydrogen bonding. So this is an everything molecule. It has everything in it. Every single force is present in this particular molecule. Okay, now let's see NH4. Okay, so you just do the tallies. And that's basically all of those. We're not going to do every one of these, but I will do the last one. And I'm going to clear that. And we're going to do the math first. Okay, well, no, not the math, but the crude sketch. So you have carbon in the middle, which you have chlorine, 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 and you have a hydrogen. Then you have bonds, right? Oh, okay, sorry, that's a bond. This one kind of went a little far, but that's a bond. Anyway, so that's for this guy. All right, so the calculations, how are they going to look like? Well, this is how they're going to look like. Going to have one carbon in group 4. You have one hydrogen in group 1. And you're going to have 3 chlorines in group 7. Okay, that's a total of 12. We're subtracting 8 from it because we have 8 electrons around it, right? Boy, 7 times, oh, okay, sorry, that's 21. I was like, wait a minute, something's wrong with this picture. That should be 26. Okay, sorry about that. I did not multiply. All right, 3 times 7 is 21. All right. Yeah, that's 26. Minus 8 is going to be what? 16. Well, 14, right? Am I right? No. 18. Boy, I don't know how to add. Okay, so there you go. So we have 18 left. What do we do with them? Remember, we put them around the central atom. I mean, the bonded atoms first. We fulfill their octet. And this is 8 right there. And this is the last 8. And we run out. And we're fine because hydrogen should never, ever have that. Never, 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 never. This is wrong. Okay. So we are good. That's a perfect structure. Okay. So now we need to write down all of our stuff. So that's our crude sketch was the one before, and this is our full little structure. Okay, so we have 4 groups, right? We still know that this is tetrahedral. Nope, tetrahedral. I forgot I copied it. Let me copy it so I don't have to type it up so many times. Okay. Right. Come on. All right. And then this is still 4 because there's still 4 bonded atoms. So that means that this is an AB4. And again, tetrahedral because nothing changed. And this is 109.5. And do we have resonance structures? None. Do we have polar or non-polar? You would probably want to say non-polar, but remember that hydrogen is different from the chlorines. So that is polar. That means our forces are London dispersion always, doesn't matter what it is, and dipole-dipole. We do not have hydrogen bonding. We could induce, and that's why I like to put it on there, ion dipole. We could induce it if we had a charged molecule around. So that's why I put it in red, so that you know that it's not part of the molecule, but it could be done. It could be done by it, because if it was a sodium chloride around here, let's just draw this. Let's say we had a sodium chloride. It would dissociate, and the sodium, which is the positive, would bond with this guy, and the chlorine would bond with that guy. So yes, we would have an ion dipole, you see, because it would induce an ion. But it itself doesn't have one. All right. All right, so let's clear all of those and keep going. All right. So, okay. I need my mouse. That's why it's not letting me close it. Yeah, I don't want to cancel that. I'm going to bring it down. There we go. All right. So now the next thing to do is balancing equations. To balance equations, you have to watch what you're doing. Balancing equations is an important part of chemistry. The main thing about it is to know what each thing is. So let's look at it. If we have an equation, we first have to know some terminology. All right. And this right here, this side, I'm just going to write it up here. This side right here is known as the reactants. Oh boy. I am telling you, today my fingers are going the wrong way. And this side right here is known as the products. Okay. This right here is the arrow that says yields or produces. Oh boy. All right. Jeez. Okay. So this right here. Now I'm just trying to put it right on top of where, oh, there we go. There we go. And then on the bottom, I'm going to put what these other things are. That 2 right there is known as a coefficient. Yes, there we go. And then this right here, I'm going to put it on this one. Right here on the bottom of this one. That is known as a subscript. Okay. All right. So what does a coefficient do? Coefficient just multiplies what it's in front of. So that means we have 2 wires, 2 potassium hydroxides, 2 potassiums, 2 potassium ions in this case. And what does the 2 mean? The 2 means that instead of having 2 hydrogens, we do have 2 hydrogens, but they're not like hydrogen. Instead, they're like this, and we only have 1 of those. You see that? So that's the difference. So this is 2H, and this is H2. See the difference? They're bonded. These are separate. Okay. And don't forget that I gave you the ones that are always doubled. It's what I call Brinkelhoff. I'm just gonna draw it. So Brinkelhoff, so it's bromine, iodine, nitrogen, fluorine, hydrogen, oxygen, and fluorine. These all come in 2s. You will always see them written as a diatomic molecule. Okay, but they're elements, but they're always like that. You notice potassium's not among them, but oxygen and hydrogen are. So if you see them written, they're going to be written as double like that. Okay, so let's clear. All right, so how do we know? So there are two methods. I like, this is not my favorite method, but I'm going to show you the way to do this. All right. So we're going to analyze this already balanced reaction. All right. So in order for it to be balanced, okay, you have to, and I'm going to go ahead and clear or just put it in red. And then we'll put it back in the right color. But these two right here, they're going to go a different color right now because we haven't yet made these happen, okay? So when we make them happen, they're going to go back to black. All right, so forget they exist. So right now, how many potassiums we have on the right, on the left, sorry, one. And on the right, we also have one, right? On the right, we have two hydrogens. And remember, we're not looking at that two yet. And on the right, on the other side, we have 2 plus 2. So I like to put 2 plus 2. It's not that I don't know that's 4. It's just that they're separate. So whatever you do to one side is not going to affect the second one. And then on the right, we have 2 oxygen. No, we have 1 oxygen and 1 oxygen. Okay. So as you can see, the first thing that is not balanced is the hydrogen, right? So in order to balance the hydrogen, we have to tackle, oops, and I said 2, I mean, that's 1. We have to tackle the one that's odd because the hydrogen is an even number on the left. So if we were to multiply this one times 2, right, that would become 2. So therefore, this one needs to become a 2 now. See how I did that? Now, that affected the hydrogen and the potassium. So we need to rewrite this is 2 and this is 2. See, now they're not balanced anymore. Okay. So the next thing we need to look at is we have 4 here. So what do we do to this 2 to make 4? Well, we multiply times 2. Therefore, that becomes a 2. And then the last thing, it also makes the, I'm sorry, not a 2, a 4. 2 times 2 is 4. And then this one also becomes a 2 because you just multiplied it. Remember, what you're multiplying is everything that's in front of it. Right. So the only one that's not balanced is that potassium. And you should always leave the elements that are alone last. And so there you go. So we have finished. And you notice now we have a 2. And this is how we started, isn't it? See, it was already balanced. But it took this to do it. All right, let's do the same thing with this one. Like I said, I do it a little different way, and I'm going to show you the other way. This is what they call the tally method. I like the inspection method. It's easier to look at things than to try to balance them all, to me. This requires you to be very disciplined, and whenever you put something in front of it, you have to change everybody that it affects. And in this case, it was everybody. So you got to remember that. I don't like that. Instead, what I like to do is I do it directly. And for this one, I'm going to do it with my fingers. All right, so I'm looking at these and my eyes go directly to this one. Why do they go to that one? Because that one exactly contains almost every element in the others, right? Almost everyone. All right, so we have the sodium. We have 1 sodium here. We have 1 hydrogen. We have 1 hydrogen here. And we have 2 hydrogens there. We have 2 hydrogens. And then we have 1 chlorine. We have 1 chlorine. This is balanced. It's already balanced. So we don't need to touch it. Okay. So that was my inspection method. I just counted. That's all I did. Now, for the next one that we have, sorry, let me clear that. Okay. For the next one that we have is potassium. Okay. So you can readily see that the oxygen is not balanced because you have 3 on one side and 4 on the other. All right. So my first thing is you always look at the most complicated molecule first, and that's that one, because it has more atoms. It has actually 1 atom of potassium, 1 atom of nitrogen, and 3 atoms of oxygen. So if you put a 2 in front of this, right, that becomes 2 atoms of potassium, so you need 2 there, right? You have 2 atoms of nitrogen, check, and you have 2 times 3 is 6, 2, 6 on this side for oxygen, and 2 times 2 is 4, and then you have 2 more, and that is also equals to 6. So this is balanced now. You see that? Just by doing what I did, this is all balanced. You do not have to change anything else. You just needed that 2 there. All right, next one. Okay, this one's already balanced, and they wanted you to do that. But instead, what we're going to do is we're going to show you how to balance it. When you see this type of equation, and this is a hard one to balance, by the way, but the reason it's hard is because of its nature. And since this particular equation is a combustion reaction, how do we know it's combustion? Well, we have oxygen on this side, and our products are carbon dioxide and water. And we have a hydrocarbon. Hydrocarbon is carbon and hydrogen only. All right, so what we need to do is we inspect this guy, and we say, this hydrogen, which is gonna end up here, right? And whatever we put in front of it has to be an even number because that oxygen is even over here. So if that number divided by 2, right? So just think about it, because we're dividing it by 2 because we have 2 here, right? So if that number divided by 2 is even, then we're okay. But if it's odd, then we need to double it, and it is odd. So we need to put a 2 there. Okay, so that 2 divided by 2 is 1, so that's an odd number. We put a 2 there. Now that immediately tells me we have 2 times 2 is 4 carbon dioxide. So we need to put a 4 right here. All right, now the last thing to do is to balance the oxygens and the hydrogens. All right, we have 2 times 2 is 4. And we already have 2, so we need a 2 in front of that. Okay, so now let's tally. 4 times 2 is 8, plus 2 times 1 is 2. That gives us 10 oxygens on this side. So we know to put a 5 right there because 10 divided by 2 is 5. And there you go. And that's how we knew how to balance it. So you see, it's the same thing we just did. This one's also already balanced, which bothers me, but okay. But this is why this one's not doubled. Remember, I told you, you inspect the hydrogen on the hydrocarbon, which is this guy. And if you divide that by 2, it is A4. So that's an even number. So we're okay to use it like it is. All right. So the first thing we need to do is to balance the carbon, and that's a 4. Then we balance the hydrogen, and that makes it a 4 because 4 times 2 is 8. All right. Now, 4 times 2 is 8, plus 4 is equal to 12. And then you divide it by 2, and then you put a 6 there. See? So that is how you know how to balance that one. This one, let's look at this one. This one's a pretty simple one. This next one and the last one. Okay, so let's look at the first one. You can readily see that the oxygen there's 2 of, and there's only 1, because you always use the more complicated one to compare against the others. So you know you're going to need a 2 in front of that, and that's going to give you two mercuries and 2 oxygens. And there you go, it's balanced. Now this last one, you have to look at it. Okay, you have one. Look at either one of the 2 of these, right? And compare them. Okay, so let's compare the silver since it's the first one. Okay, we have 1 silver and we have 1 nitrate. Remember, these are groups. So 1 nitrate, 1 nitrate, 1 silver, 1 silver. Okay, one chlorine, one chlorine, one sodium, one sodium. Okay, so this one's already balanced. We don't need to do anything with it. But this one did need the 2 and the 2, right? Okay, so that's all. That's how you learn to balance. Now, it always is helpful when you're balancing to know what kind of equation you have, what kind of reaction you have, and that's what we're going to look at next. Right here, these are the 5 types. You have synthesis, you have decomposition, you have single replacement, double replacement, and combustion. For those, we're going to look at the PowerPoint real quick, like, hold on, there we go. And then we're going to use the classified balance sheet. Okay, so for this one, we have these. We have anything that burns requires oxygen. So remember the things that I'm going to tell you. If you have oxygen over here, right, as one of your reactants, and your products contain oxygen, right? So you have oxygen right here, and your products contain oxygen. You see that? Then you have a combustion, right? So that's our first one. It's called combustion because to combust or to burn, you need oxygen. Just remember that. All right. And here's the key that I was telling you. And if they're hydrocarbons, more specifically, they will form carbon dioxide in water every time. Okay, look at this one. Sodium plus oxygen. You can readily see that that is going to be NaO. But remember, you can't. One of the things that I showed you how to put compounds together, remember? Sodium is a plus, oxygen is a 2 negative. So you're going to end up doing Na2O, not NaO. So this is Na2O. Okay. And that is a product, right? And it contains oxygen, just like I said. So that is what you want. Okay, that's clear. Of course, it's not balanced, but we're going to do all that here in a minute. Okay, so, all right, so to balance it, what would you need to do? Well, you look at the most complicated first. Sorry. You look at the most complicated first and you add coefficients. In this case, you would have to add a 2 because the oxygen is not balanced, which makes this a 4. And there we're done. You see that? Clear. Okay, so let's keep going. And let's see if they balanced it or not. Yeah, they did. Okay, so clear that. All right. And here's another one. Okay, this is a combustion also. We're going to end up with carbon dioxide and water. Okay, so to balance it, remember, look at your hydrogen and your hydrocarbon first, right? If divided by 2, because you have 2 here, right? That gives you an even number, then you use that. And then you want to balance this part, right? Okay, so 3 times 2 is 6, and 4 times 1 is 4. That gives me a total of 10. 10 divided by 2 is 5. And that's how you balance it real quick. And let's see. Come on now. 3, 5, 3, 4. All right, synthesis. Okay, so this one, what you're doing is you're combining 2 simpler substances into one product. Sometimes you may get a little tail, and you'll see what I mean by that, but it becomes usually a one product thing. Okay, so when you have a synthesis, this is one right here. You are getting hydrogen gas and chlorine gas and becoming hydrochloric gas. So hydrochloric acid, no, this is actually hydrogen chloride gas. Products. If they're ionic, your charges are going to cancel. If they're covalent, it's much harder to tell what your products are going to be. So in this case, these are ionic. Remember, you do your ionic charges. This is a +3. This is a negative. So this is going to be AlCl3, right? And in order to balance, you look at this one first and see, okay, that's an odd number, so I need to put a 2 in front of it because that's an even number. So that gives me a 2 here, and that's a 2 there. See? And that becomes a balanced reaction. Now let's clear that and go back and look at it closely. Okay? And there you go. All right, decomposition. That's when you're breaking up. Remember, decompose means to break down, break up. So you have one reactant that becomes multiple products. Example, water when it's hydrolyzed. Okay. If they're binary, they will break up into their elements. If they're not, then it's harder to know what's going to happen, and you have some rules that you need to follow, blah, blah, blah. So KBr, very simple, binary. So you're going to have potassium and bromine, but remember, bromine is Brinkelhoff, so it's going to be KBr2. So now there's no longer balance. So you will need to always compare the most complicated one against the others. And then that way you can balance much easier. Okay. And leave the elements that are by themselves alone. You notice I did the other one first. Okay. So let's look and see what happens. Okay. And then single replacement is when one element replaces another in a compound. Remember, a positive will always replace a positive, and a negative will always replace a negative. That there are rules by which these go, and we'll look at those here shortly, but this is how it's going to go. So you notice that A is going to replace that B in there, and the B is going to be booted out, and it is by itself right there. Okay. Okay, here's an example. Copper and silver nitrate. Copper is a stronger, more reactive metal than silver. So copper is going to boot out the silver. See how the silver is accumulating here? And that's pure silver there. And the copper is now being joined with the nitrate ion. So you get copper nitrate in silver. Now, is this balanced? Yes, it is based on that. You can see it is. So you're going to have the products, you're going to have a metal that is in the compound, now that is out of the compound. And if it's a nonmetal, same thing. And the free element has to be more active. You look at your activity series, and I have that activity series out there. So here we go, iron and copper. Iron is more reactive than copper, so this reaction really this reaction will happen. Iron is more reactive, so yes, it will happen. But bromine is not more reactive than chlorine, because if you look at the periodic table, and this is only the halogens now, but if you look at that periodic table, bromine is below chlorine, which means it's less reactive, therefore no reaction. Okay. And double replacement, now you have, they change partners. Basically, the positive of one and the positive, the other switch places. Or if you want to call it the negative of one and the negative of the other switch places, either one, it doesn't matter. But they do switch places, period. All right, an example is right here. Look, this is lead nitrate and this is potassium chromate. When they get together, you form potassium chromate and, lead nitrate becomes lead chromate, and potassium chromate becomes potassium nitrate. See how it becomes different? Okay, so lead chromate is insoluble. That's what the S means. That means it's solid. That means it's never going to be in solution. And that's what you want. You want one of these to become a solid or a gas or something and fall out of solution. Because if it didn't, it would stay. And you would keep doing switch, 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 switch all the time, and no reaction would ever happen. So for that, you have to know your solubility rules, your solubility table. Hold on a second, somebody's at my door. Okay, sorry, here I am. Okay, so potassium nitrate and lead nitrate, lead 2 nitrate in this case, and potassium iodide are going to join together. And are they going to react? Yes, they are, because potassium iodide, lead 2 iodide is solid and potassium nitrate is not. So one of them is solid, therefore one of them falls out of solution. And there's your balance. And then sodium nitrate and potassium iodide. Okay, both of these are going to be soluble because sodium iodide and potassium nitrate are both going to be soluble. Therefore, the reaction will not happen. And that's how that works. All right, and that's your 5 types of reactions. So now we're going to apply everything we learned to one thing, which is known as classify balance. Okay, so this one, we know some things already. So we're going to answer these questions real quick. Okay, so a chemical reaction is what? Okay, this is products change into reactions. That's a true statement. The law of conservation applies. Yes, that is a true statement. That's why we balance. Substances change state, they can. So it is all of them, right? So we put a D right here. During a chemical reaction, what happens? New elements are produced? No, no elements. Atoms are rearranged? That sounds right. Destroyed or created? No, because the law of conservation of mass says that nothing is created or destroyed, only rearranged. And there you go. An equation is balanced by doing what? Remember, I told you, you cannot change the subscripts. You can only add coefficients. So the answer is B. You can never, ever erase elements because you're playing God there, or change subscripts. You're creating a compound that didn't exist to begin with in the equation. So no, you can't do that. So an atom's ability to undergo chemical reaction is due to its outermost electrons. That's why we learned how to find the valence electrons, which is what that is. What are the reactants in this equation? Okay. Reactants are on the left, remember, so zinc and copper 2 sulfate, so C. And the products are zinc sulfate and copper, so it's just B. All right, so that's that one. All right, now, first thing we're gonna do is we're going to classify them. And I'm just gonna put initials instead of writing the whole word. All right, so let's look at what's going on. Zinc is replacing hydrogen, you see that? So this is going as a single replacement, okay? Now let's see if it's balanced. Okay, we have two hydrogens, one sulfate, one zinc. Yep, this one's balanced. So you can just put here balanced. Okay. This one Okay, this one is a decomposition. See how one thing is becoming two things? Okay, so that's what this is. This is a decomposition. Let's balance it, right? So we have two hydrogens, one carbon, and 2 plus 1 is 3 oxygen. So no, this is also balanced. Okay. All right, so next we have, okay, this one, what's going on is the calcium and the hydrogen are switching places. You see that? So this is known as a double replacement or double displacement, however you want to call it. All right, so calcium, chlorine is not balanced. See, you got to compare the most complicated one first, and that's that one. So I say we need a 2 right there because there's a 2 here. You see that? All right, so that 2 needs to be put here. Now you got 2 chlorines also, right? So this is balanced. The calcium is balanced and the carbonate is also balanced. So that's balanced now. All right, so we just changed it. And let's make this red so we know we added that. Well, we should know we added it because I said make it red. Make it red. I want it red. There we go. All right, so the next one, let's look at it. Okay, see, zinc is being replaced by silver. You see that? I mean, sorry, the opposite. Zinc is replacing silver. So yes, this is a single replacement. And is it balanced? No, very obviously not. We are looking at this one because this one's got the most, right? And by looking at this, you can see there's 3 NO3s and there's only 2 here. There's only 1 here. So, I mean, 2 NO3s and there's only 1 there. So we need a 2 in front of that. That 2 needs to be red, like I said. Okay. And now we have 2 silvers too, right? So we need a 2 in front of this silver. And also red. Okay, and that's how you do it. That is all of them. All right, and the zinc is balanced already, so everything's good. All right, next one, if you look at it, you have oxygen on the reactants, and there's oxygen in the products. This is a combustion reaction. Always look at, like I told you, always look at this hydrogen. The hydrogen is divided by 2 is an even number, so we can actually go ahead and proceed and put a 4 right here. Make it red though, just so that we know that we put it. All right, that 4 is good. Now the 3 is telling me we need a 3 in here, right? Because we have 3 carbons that we haven't balanced. Now, this is where we look at the math. So it's 2 times 3 is 6, right? Because 3 here is multiplying that, and that's a 2. So 3 times 2 is 6, and 4 times 1 is 4. So 6 plus 4 is 10, divided by 2 gives me a 5, which is what needs to be here. And now we have 10 oxygens on both sides. Next one that we're looking at is this one, and this is also a combustion. Once again, you have the same thing. You have oxygen and carbon dioxide and water on the other side. Now, this one, I'm going to caution you because we have an extra hydrogen. We are not going to do that division thing. Okay. Instead, we're just going to look at it. And we have an extra oxygen, see? So that makes things even. Well, sort of even, not really. They're both odd on both sides. So that's why we're saying it kind of makes it even, though they're not really even, but right here, that's a 2 carbons. All right. And then we have 5 plus 1 is 6. So we need a 3 right here, right? because you already have 2. So remember, we are multiplying. When we put this in front, we're multiplying what's in front of it. So 3 times 2 is 6, and 3 times 1 is 3. So that's how many hydrogens and oxygens we have in this water with the 3 in front of it. Over here, we have 6 hydrogens because 5 and 1, right? That makes it 6. Now, the last thing to be balanced is our hydrogens. How do we do that? Well, I'm going to go ahead and write down the tally. So 2 times 2 is 4, and 3 times 1 is 3. So that gives me a total of 7. On this side, we have 1, so we can say 7 minus 1, right? Because this is already used. That gives me 6 divided by 2 is 3. So that's how we know to balance. Now let's clear all these drawings, and we just know we need a 3 right there. Here, okay. Just need a 3 right here in red, and that's all. And we have actually balanced. Oops, I don't want all that red. Just this. Okay, we have actually balanced all of these now. Now it says write a balanced equation for each of the following reactions and tell which one, and of course you need to tell which kind it is. All right, so we got, notice it says is the product. That's a key word. That means it's going on the other side of the reaction. So the actual reaction is magnesium and chlorine. Okay, so we got Mg plus, and the plus just means adds to, right? Chlorine, and remember chlorine is diatomic because it's part of the Brinkelhoff people that we were talking about. Let's go home here. Okay. There. All right. So with this in mind, right, we need to remember that we have an arrow. And when I do arrows, I just put two like that, and it makes an arrow. Okay. And this is going to be MgCl2. Why is it MgCl2? We have to remember all of this that we learned is applicable in everything. So you just got to remember how to make compounds. Magnesium is 2, chlorine is 1. So when you cross, remember, magnesium is a +2 because it's in group 2. Chlorine is a -1 because it's in group 7. So we crossed, you get Mg with the 1 and Cl with the 2. So you notice that's already balanced. So we don't need to balance. And what kind of reaction is it? Well, if you look at it, this reaction happens to be what is known as a synthesis, right? Or in your book, they call it combination, which is fine. I mean, it doesn't matter. We're just going to call it synthesis or combination so that you know. All right. And they also call it composition. I mean, there's a lot of different names to these, but okay. Notice here again, are produced. So these are the products. These are the reactants are potassium hydroxide and copper 2 sulfate. Because you know how to name things, you should be able to put these together. So potassium hydroxide is K and OH. Potassium and hydroxide together. And then you got copper 2. Sulfate. So copper 2 sulfate is CuSO4. How do I know? Oops, that U is lowercase and the SO4 is lower. Oh, let me make my arrow first. There, so I don't have to go back and fix that because I would. Oh, nope, wrong way. Ah. Okay, there we go. All right, so these are going to switch places. So the potassium is going to get the sulfate. And the copper is going to get the hydroxide. And how do I know to do all that? Well, I'm going to show you here in a minute. So when you decompose these two, and this is what you should always do, should decompose them into their ions. So you're going to get a K plus and an OH negative. That is going to bond to a copper 2 plus and an SO4 2 negative. See that? That's what you have on the right. Now on the left, when you bond them, you're going to get this K bonded to this SO4. You see that? So it's going to be K2SO4 because you got 1 and 2, right? So the 2 goes to the potassium and the other one goes to the, all right? So that's how you know. And then the copper is going to bond to the OH. So the copper is going to give its 2 to the OH, see? So that's why we did. All right, so let me go back to the home and home and make these corrections here because these are bad. I gotta have them correct because otherwise, and then we're gonna balance because it's not balanced either. So we gotta do all that. And that's why I want these as subscripts, not as big numbers in front so that you can know that there's a difference. All right, so a subscript tells us how many atoms, not atoms, how many molecules or whatever it's placed in front of, particles. Let's call them particles. How many particles of that thing there are? The subscript tells us how many atoms are in that compound of that element, okay? So let's clear this. And now that we have the equation, we can write in the, okay, you can always look at this one. This is the most complicated one of all. You notice there's a 2 there. That means we need a 2 in front of this one, don't we? And that 2 now has OHs, and that's OH there. Okay, so it's balanced. That was all it took. Sometimes it's easy. And what is the name of this equation? Well, based on what we did, this is a double displacement, right? And it is a double. It is what it is. It is a double displacement reaction. So we'll just call it double or replacement, sorry. Some people call it displacement, some people call it replacement. It doesn't matter. It's one and the same. All right, and there you go. And that's how you do all of these. All right. So now I know we're moving at a super fast and furious pace, but you can always go back and watch this video that we're recording for you later. All right, and the last thing is moles. All right, so moles are something that is important to know because moles are the one thing in chemistry that uh, that are, of course you can, that are molar mass. So in order to do moles, you have to know how to do molar mass first. So let's do that. Like I said, moles is a counting number. So basically, you know what a dozen is because you've always heard a dozen, right? A dozen is 12. There's 12 things in a dozen. 12 things, whatever things, it doesn't matter. But that dozen is not always going to be the same because let's say you have 12 sheets of paper versus 12 tables. Which one do you think would weigh more? Obviously the tables, right? Well, same thing with moles. It's not a mass number, it's a counting number. So the count is 6.02 times 10 to the 23rd particles or whatever's in 1 mole. All right, so for this one, we're going to do it really quick and we're going to just add. All right, so the name of this one, and I did this on purpose because I wanted you to Sodium sulfide. Okay, so the mass of 1 mole is going to be like this. You're going to have 2 times the mass of sodium in the periodic table, and you want to use every bit because we're not doing protons, neutrons, electrons, right? We're doing mass, and mass is very particular. Okay, so that's the sodium, and then you're going to add the sulfate, which is the sulfur, which is 32.07, if I'm not mistaken. Yeah. And then that's going to give you the number, which I have my calculator. Yeah, there it is. All right. So in this case, you're going to have 22.99 times 2 plus 32.07. That gives me 78.05. And when we are talking about molar mass, this is our unit, grams per mole. Okay. So we can just copy that and just use it. Grams per mole. And we're going to, okay, there we go. Always use that. Grams per mole of what? Per mole of sodium sulfate, okay? Sulfide. Wow, where's my L? Okay, so this one is ammonium chloride. Okay, so for this one, you're going to have to tally 14.01 from the nitrogen plus, you got 4 times 1.01 from the hydrogen. Oops, I said plus and I put equal. Plus, sorry. Okay, and then you got another plus, because we still have chlorine, right? Which is 35.4. All right, so we add all of these up, and that's going to give us our total. And our total is I get 53.5. And remember, it was grams per mole. Okay, 53.5 is what I got. Yeah, that seems about right. All right, the next one is copper 1. How do I know it's copper 1? Because fluorine is. All right, so copper, you have 1 copper and 1 fluorine. So copper is 63.55. And fluorine is, oh my God, my finger is not hitting the right thing. Fluorine is 19 even. That is 63.55 plus 19. It's like adding 20 minus 1 is 82.55. And that is grams per mole. Okay. Now this next one is copper 2 fluoride. Oops. Copper fluoride. Damn, where's my O? Okay, there we go. And this is wrong. I just noticed that that's in the wrong area. Okay, there we go. All right, so in this case, you have 263.655. Okay, so that's going to be 2 times, right? 63.55 plus 19, which is equal to 146.1. There you go. Okay. Now, this is gonna get a little more complicated. So this is lead 2 sulfate. Okay, so for this one, you're gonna do lead, which is 207.2. You're gonna have 1 sulfur at 32.07, plus you're gonna have 4 oxygens at 16 each. Okay, and that is equal to, so let's add up all this, right? That's what I'm saying. This is equal to, so we're adding it all up. So it's 207.2 plus 32.07 plus parentheses 4 times 16. And that gives me 303.27. Okay, now this one is giving us our name, so we need to figure out what nickel 2 chloride is, NiCl2, right? That's what it would be. All right, so from that, see, it's important to know the formula. And this is supposed to be, there we go. All right, so nickel 2 chloride is telling me we have 1 nickel, and nickel is 58.69 plus we have 2 chlorines times 35.445, and that is equal to, well, let's see, 35.45 times 2 plus 58.69, did I say? Yeah. 129.59. That is grams per mole again. Copper 2 nitrate. Okay, so we got copper. And we have nitrate. Nitrate actually is NO3. And we have a 2. Okay. So let's fix these so that they'll be in the right spot, because they're not. Okay, and that's that. All right, so you can see that there's 1 copper, right? And the copper is 63.55. Then we have, this is where it gets a little different. Okay, so that 2 is multiplying both of those. So the nitrogen is 14.01, right? And then you have the oxygen, which is 2 times 3, so you have 6 oxygens at 16.00. Okay, and that is equal to, let's see what it is. So we got 63.55 plus 2 times 14.01 plus 6 times 16. And the answer is 187.57. And of course, that is grams per mole. All right. Next one is dinitrogen pentoxide. So, N2O5. It's not O. Oh, not that O. O5. Not that low. Short. All right. So once again, we have 2 nitrogens and 5 oxygens. So you just put that to the side, right? And say 2 nitrogens. We're going to have 2 times 14.01 plus 5 oxygen, so 5 times 16. That's going to be equal to 14.01 times 2 plus 5 times 16. 108.02. Okay, sulfurous acid. So that is H2SO3. This is sulfurous, comes from sulfite. And sulfite is SO3, not SO4. And we have the same thing. So we got 2 nitrogens times 1.01. And we have to add it to 1 sulfur at 32.01. 07. Not on that. Okay, plus we have 3 oxygens times 16. All right, and that is a total of 2.02 plus 32.07 plus 3 times 16. 82.09. Grams per mole, and this is a 3. So, okay, this it didn't work. And this is hydrosulfuric acid, so H2S. And remember, in order for this to be the acid, it has to be in the aqueous form, so you just gotta always indicate that. All right, so H2S is easy. It's just 32.07 plus 1.01. So it's 33.08, right? No, 2.02. 34.09. Let me see again. Yeah, 34.09. And that is grams per mole. Okay, so that's how you do them. And now the next one, you got ammonium phosphate. Oh boy, this one's going to be fun. This one's NH4, 3PO4. This is longer. And they're getting more complicated, you know? So we're getting a little bit more into the thing, which is fine. That's exactly what we need. We need to get a little more complicated. Why do we need to get more complicated? So that anything anybody throws at us, right, we can handle. All right, and then is now you gotta look at it. All right, so you got how many nitrogens? You have 3, right? So 3 nitrogens at 14.2. Then you have, and then you have 3 times 4 is 12 hydrogens times 1.01. Then you have 1 phosphorus at 32, if I'm not mistaken. No, 30.97. I don't know what. 30.97 plus 4 oxygens times 16. So all of this needs to be added to get this molar mass. All right, so let's do it. Okay, so 3 times 14.01 plus 12 times 1.01 plus 30.97 plus 4 times 16. And the answer is 149.12. Sounded like it was going to be heavier, didn't it? But you never know. All right, the next one is nickel 2 sulfate hexahydrate. So this is interesting because it's nickel 2 sulfate, which is SO4. But then you have hexahydrate, which you put a dot and you put 6 waters. So let me get the things where they belong, so we'll know what to do with them. The 6 is still big because it's a coefficient. Okay. Now, 1 nickel, and nickel is 58.69, plus we have 1 sulfur, oops, plus we have 1 sulfur, which is 32.07, plus we have 4 oxygens times 16. I'm sorry, 0. Then we have more. Then we have 6 waters. So we can do this 2 ways. We can tally the water and then multiply it times 6, or we can, normally what they ask us to do is to do it this way, and you'll see why in a minute. So water is 1.01 times 2, so that's 2.02 plus 16 is 18.0. So we're gonna say 6 times, oops, I forgot the parentheses, 18.02. That's how many waters. All right, so this is our answer. So we got 58.69 plus 32.07 plus 4 times 16 plus 6 times 18.04. I mean, 0.02. And the answer is 262.88. And that is grams per mole. And there you go. That's all of them. So we have done, why does it say 10, 11, and 12? That's weird. That should say 11, and the other one should say 12. That was weird. It was like they were out of order. Did you see that? Anyway, so there you go. So that's how you do molar mass. Molar mass is pretty simple. Now, why do we need molar mass? Well, we need it for moling. Anything that we have to do mole conversions. Okay, so we're going to do a diagram here that's going to help you convert. Okay, this mole conversion diagram is very important. And we're only going to go across. The second half goes up and down. But we're just going to go mass in grams to moles to particles, right? And particles to moles to grams. And grams to moles and particles to moles. But you notice moles is always the central. So you always have to convert 2 moles in order to convert from one to the other. All right, so remember that. All right. So we are going to do mole conversions. And this is all of it, by the way. All right, so the answers are already here. The point is not that you don't have the answer. The point is that you get to the answer, right? And this is practice. So I figured if you had the answers, that would be better. So what we're going to do is we're going to insert a table. Let's just make it 4. I don't think we'll need more than 4. Undo. Where is it? Oh my gosh. No, and go back to the document again. Okay, no, back. There we go. I need this undone and I don't know how to undo it. So I just said, oh, that's because it got huge and I need to erase it. All right. I said I'm inserting it here and it didn't go there. I don't know why. Okay, now it will insert in the right spot. Okay. So how are we doing? Okay, we want to calculate atoms. You see that? That's what they're asking. They're giving us grams. So we need to put what we know And platinum is PT, so I'm just going to do that. So for every mole, see, we have to go by moles, remember, of platinum. In the periodic table, platinum is 195.08. We have 195.08 grams of platinum. And they want us to convert to atoms. So this is where the conversion happens. 1 mole of platinum contains 6.02 times 10 to the 23rd atoms of platinum. Now all we do is multiply, right? And we got it, right? So clear everything, and then just do all the top multiplies and divide by the bottom. So 2 times 6.02 second EE23 equals, and then divided by 195.08. And the answer I get is 6.17 times 10 to the 21. And guess what? That's exactly what we got. So this is the way to get it. We don't need this one, so I guess, erase that. There. I just put 4 just in case we needed them, but there you go. And that will give you that answer. Right. So same here. You insert, I like to insert this little table because it helps me get there and you see and follow. All right, so we have this table. It says a metric ton. Okay, and the way, by the way, we had 3 sig figs is because we had 3 sig figs here, right? 3 sig figs on the first thing right here. So we have 3 sig figs on the answer, right? This one should say 1.00, by the way, and that's something I keep changing. All right, so we have put 1.00 times 10. You know, why not just copy it? Be easier, huh? Because now I don't have to worry about putting my there. All right, it says how many atoms are there? Okay, of sulfur, right? So for every 1 mole of sulfur, and we know this because we know the periodic table, we have 32.07 grams of sulfur. So see, right now, you can see that that sulfur grams is going to cancel. Now we need something that will cancel the moles because that's not what we want. And for that, we have the same thing as this, right? So we're just going to copy that. And then of sulfur, right? Atoms of sulfur. All right, so we really don't need this again. Let's get rid of it. All right. So we multiply, divide, and our answer, when we multiply, divide, remember it's going to be 1 second EE to the 6 times 6.02 second EE to the 23rd. So those two are going to add and become 29. And divided by 32.07, that's going to lower it to 28. Then it's 1.877 times 10 to the 28th. And since we had 3 sig figs, we keep to 1.88 times 10 to the 28th atoms of sulfur. See? All right, now the next one is grams too. So then we have grams, but we want atoms. So it's backwards, right? You notice here we had atoms and we had grams. I mean, we had grams and we wanted atoms. Here we have atoms and we want grams. So it's going to be the same thing, except backwards, right? So let's insert a table. And this time, let's just make it 3 because I know I don't need 3. All right, so we're going to take this. Which is the question, and mercury is this, so I'm just going to use that. So for every mole of mercury, see this time mole goes on top. Why? Because we want atoms on the bottom so that we can cancel. Oh, I can just grab this. I mean, it's make my life easier, right? Might as well just do it. Okay, of mercury. All right. So the next thing to do is to get rid of moles. So 1 mole of mercury on the bottom, right? Because that way we get rid of it is equal to mercury, where are you, Hg, there you are, 200.59. So this is 200.59 grams of mercury. Okay, so we do the math. This time we have to multiply 1.19 second EE 23 times 200.59. You hit equal and then you divide it by 6.02 second EE 23. And if you look at 23 and 23, they're going to cancel. So you're just going to get a number. And that is 300, I'm sorry, not 300, 39.65. And we only had 3 sig figs, so it's 39.7. And that's exactly what we got. You see? So are you getting this? Yes? Okay. I'm not going to do that one. I'm going to do one of the bottom ones each, and that's it because we're running out of time. So I'm going to put it here. Okay, so we're going to insert. Probably we don't need, oh, what? What happened here? I want to insert a table and it won't let me. Is this it? Yeah, I think this is it right here, isn't it? Nope, it just went away. No, yeah, there we go. We're gonna insert a table. 3. I wouldn't even need 3, but okay. See, it wants the number of moles in benzene. Okay, so 17.2 grams of benzene. So C6. I'm just gonna copy this. Rewrite it every time. Okay, is equal to, so 1 mole of benzene. This is why we needed, oops, 1 mole of benzene. This is why we needed molar mass, you see? So now we know that 12.01 plus 6.06, okay. So we got 6 times 12.01 plus 6 times 1.01. And that gives us 78.12. All right, and that's all really we need. We don't really need these right here, do we? All right, so we're just multiplying and dividing. So multiply, there's no need to multiply. So it's just 17.2 divided by 78.12. And that gives me 0.22 moles, 220, because we need that 0. Because it's 0.22017. So it's 0.220 moles of benzene. And there you go. Now I'm going to do it backwards, where it coming the opposite, right? So we need to do the mass. No. Okay, the moles. We did the moles, but now we need the mass. Yeah. On tin 2 sulfate, why not? Okay, so let's do this one. Let's insert. We're going to only need 2 actually. All right, so we're just going to copy this guy. And we're going to say 0.187, right? Moles of this guy. All right. For every mole of that guy, we got I don't know. We have to do math. All right, so for every mole of tin, right? Tin 2 sulfate. So we got to do the math. And we can do that here. We can do, oh, you know, that's something I should have done right here. To do the molar mass of this one, you had to do 6 times 12.01, which is what I told you, but I didn't say it out loud. Plus, I mean, I didn't write it. I said it out loud. I did not write it. 1.01. Oh, 6. 6 times 1.01. Okay, and that's the answer is what we got, which was 78.12 grams per mole. Okay, and that's that. Oh, that's illegal. Okay, now we're doing the same thing with this one. Okay, so we got 1 tin, and tin is 118.71 plus we have 1 sulfur at 32.07, right? Plus we have 4 oxygens times 16.00, and that's equal to, I don't know, let's see. Here is 118.71 plus 32.07 plus 4 times 16.00 is, oh, clear. Dang it. How did I do that? 4 times 16, okay. That gives me 214.78 grams per mole. So this is grams per mole. See, grams per mole. All right. So when we do the math, oops, sorry, that should have been 214.78 grams per mole, right? All right. So that's how we know what to put up there. 1478. Yeah. Okay. So when we do the math, we just multiply. So we're multiplying that number we got times 0.187. And we get 40.16386 blah 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 grams of tin. So it's 40.2 because we need 3 citrics, and that's it. That's how you do these. Okay. So now percent composition is a little different. Now this one I gave you the math, and I gave you everything right here. So sucrose has this formula. Okay, and so the formula you write down. See, I did that. Okay, and it gave me that, right? So this is your formula. So what you want to do for each one of these is I'm going to show you with my finger with this one because it'd be easier. Oops. No. Sorry. Just my thing just went away. Okay. So this one, okay. So each time that you're doing a percentage, right? So like percent carbon is going to be equal to this number right here, add it. I mean, multiply it. So 12 times 12.01. Going to be 144.12. So that goes right here, 144.12 divided by the total number, which is 42.34 times 100. Okay, so percent carbon, and remember you have 1, 2, 5 citrate in this one. Yeah, you have 5 citrates in this one, but that's all right. Okay, so 1 divided by 342.34. And that gives me times 100, that gives me 42.098. So actually, we can say 42.098. Okay, percent. because we do have 5 sig in both. So we can say that here. Let me write it down here. Oh, you know what? Let me clear all of that first and write it right here. Actually, I'm gonna write it in parentheses. I'm gonna put it in officially. I get 42.098%. Okay, so that's the real answer. I lowered it, but I don't know why. All right, so then the next one is your hydrogen. But you have 22 times 1.01. So it's this one actually. 22. Okay, so that's the 1.0 times 1.01. Okay, so the answer is 22.22. 222. 222, no, not 200, 22.22. And that is divided by 340, 42.34. And then multiply times 100. And that gives me 6.4906. All right. So in this case, we only had 3 sig. So this is good. Or did we have 2? Let me see. Let me see again. Because I'm like, wait. Because sig figs are important. Yeah, you should only have 3. So it's 22.2. Yeah. Okay. So that's correct. We don't have to correct that one. And the last one is the oxygen. And the oxygen is 11 times 16, right? 0.00. That one has 4 sig figs. Oh, wait. I was right. It is. We don't need these numbers. It is 0.10. So it is right. All right. Never mind. I'm looking at it. Okay, delete that. Okay, I get 176 divided by 342.34 times 100. And that gives me 51.41, which is correct. Now, if you add up all of those, it should add up to almost 100. So if you add 42.1 plus 51.41 plus 6.49, it should be 100, and actually exactly 100. So there you go. So that's your math for you. All right, so now you know how to do all of it. You know how to do percent composition. You know how to do mole conversions. And you know how to do molar mass, of course, because you cannot have one without the other. All right, so that's that. And then the final exam, there's stuff you can look at. There's a review, lecture review. You can actually view that whole entire videos. There's 3 videos. There's this. If you turn these guys in completed, both of them, you get some bonus points for each one, for this one and for the other one, and for this one. They're both, see, it's a review that you just bring up. And how do we turn it in? You can take pictures of it and put them all in there. That's why you got like 20 files that are possible to turn in. Okay. And that's it. Unless you need me tomorrow, you can send me a text or something and I'll be here. Send me a text like earlier in the morning and I'll be here. All right. All right, then we are finished. going to post this later, as soon as I can. Jocelyn, all right, we are going.